Hello my dear children, once again welcome to our physics class. Hope you all are fine over there. In the previous session we had discussed about the characteristics of waves, that is some terms related to the waves, and also we discussed about wave equation. We discussed about frequency, amplitude, time period of the wave. Also we discussed about the equation, the wave equation, how to express a progressive wave using an equation. And I hope you remember that equation. So a progressive wave can be represented by y of xt equal to a sin kx minus omega t plus phi. We discussed each terms of that equation. Okay. We also derived an expression connecting the velocity and wavelength and frequency of a wave, that is v equal to nu lambda. So today we are going to discuss about the superposition of two waves. That is, whenever two or more waves pass through a medium, what happens? What happens to the net displacement of the wave? Okay, so let's discuss about superposition today. So the principle of superposition of waves. Principle of superposition of waves describes how the individual waveforms can be algebraically added to determine the net waveform. First we can study the statement. It states that means the principle of superposition of waves states that when two or more waves pass through a medium, the net displacement of particle at any time is the algebraic sum of displacements due to each wave. Okay, so when two or more waves pass through a media, the net displacement of particle at any instant is the algebraic sum of displacement due to each wave. So this is the principle of superposition of waves. So we can consider different cases. Consider two waves which are in phase with each other. Which are in phase means their starting point, their ending point, everything should be same. And they have the same amplitude, same angular frequency, same angular wave number. Okay, so consider this figure. Here you can see two waves. These are the two waves. See, this is the first wave and this is the second wave. So this wave is represented by y of xt equal to a sin kx minus omega t. That is a wave equation. Okay, here the wave starts from 0 or from the origin like this and progress like this. This wave also starts from the origin and progress as that of the first wave. So both the waves are in phase. Both starts together and both ends together. Okay. Now both becomes maximum together. Both becomes minimum together. Okay. And the second wave is also represented by y of xt equal to a sin kx minus omega t. So when such two waves come together or pass through a media, what will be the net displacement? So the net displacement of the wave or the total displacement of the resultant wave will be the sum of displacements of individual waves. Okay, so these are the two waves, and when these two waves superimpose with each other as they pass through a media, the net wave will have a displacement equal to sum of displacements of these two waves. Suppose the displacement of first wave is 5, or the amplitude of the first wave is 5 and the amplitude of the second wave also will be 5 because both are same waves, both are in phase, they have same amplitude, frequency, everything. So if amplitude of one wave is 5, amplitude of another wave, second wave is also 5, and when such two waves superimpose, the amplitude of resultant wave will be 5 plus 5, that is 10. Okay, now this figure shows the amplitude or superposition of two waves which are in phase. Consider these two waves. This is first wave, this is second wave, and such two waves are approaching each other. So as they approach each other at a point, both the waves will superimpose. So at this point, two waves will superimpose, and at the point of superposition, amplitude will be maximum. See, amplitude will be double, because this amplitude will be the sum of amplitudes of these two individual waves. So at the point of superposition, the amplitude of the wave will be more, it will be maximum, and after superposition both the waves will cross each other. they went back in different directions. See, this wave will go to this direction and this wave will go towards the right direction. That is shown here in the third figure. Okay, so this is the superposition of the waves when they are in phase. So what is superposition? When two or more waves pass through a media, the net displacement of the particle at any time is the algebraic sum of displacements due to each wave. That means the total displacement of the wave or the displacement of the resultant wave will be the sum of displacements of the individual wave. Now what happens if these two waves are out of phase? Okay. So consider these two waves are completely out of phase. Then what happens when such two waves superimpose? So here first you can consider this figure. Consider this wave. This is the first wave. Consider this wave, which is the second wave. See, second wave is out of phase with the first wave. First wave starts from the origin and proceeds towards the positive axis. But second wave starts from origin but proceeds towards the negative direction. So these two waves are out of phase with a phase angle of pi or 180 degrees. So the phase difference between these two waves is 180 degree. And this wave becomes maximum at this point. But at the same point, the second wave is becoming minimum. Okay. So when such two waves superimpose with each other, what will be the resultant amplitude? See, in this case, the amplitude of this wave will be A. But at the same point, amplitude of the second wave is minus A. So A minus A will be 0. So when such two waves which are out of phase superimpose each other, the displacement of resultant wave will be 0. And we can't find any wave pattern at that position, and we will get a plain result like this. Okay, so the net displacement will be 0. And the same thing is shown here. Consider two waves. This is the first wave. This is the second wave. These two waves are approaching each other. And what is the peculiarity of these two waves? These two waves are out of phase. Okay. And when such two waves approach each other, what happens? See, they are little bit closer to each other now. Again, they will overlap. Now, at this point, the first wave and the second wave overlap. But since they are out of phase, what happens? The net result will be 0. So at the point of superposition, the net displacement will be 0. We can't find any wave pattern. And after superposition, the two waves will cross each other and they will went back in different directions. So that is shown in the rest of the figures. Okay. So this happens when two waves which are completely out of phase superimpose with each other. So that's all about the superposition of waves. Now, we can discuss reflection of waves based on the superposition principle. So what do you mean by reflection of waves? Just like the reflection of light, reflection of sound, there is reflection of waves. So whenever we throw a ball towards a wall, the ball will bounce back. Just like that, whenever the waves strike a boundary, the waves will come back. It will be reflected. Okay. So the reflection of waves is the change in direction of a wave upon striking the interface between two materials. This interface means it will be a boundary. So when a wave strikes any interface between any two mediums, the bouncing back of wave is termed as reflection of wave. Okay. So reflection of wave is the bouncing back of wave. Now, this interface or the boundary can be of two types. It can be an open boundary, just like a ring, or it can be a closed boundary, like a wall or wooden block, something like that. So when a wave strikes an interface, in case of open boundary, it will get reflected as well as refracted. Okay, so when the wave strikes an open boundary, the wave gets reflected as well as refracted. At the same time, when the wave is incident on an interface of a closed boundary, it will be completely reflected. Example, wave striking a wall. It is a closed boundary or rigid boundary. So in such a case, the waves will be completely reflected. Okay, so these are about the two boundaries. Now here you can see, this is the closed boundary and this is the open boundary. This is a ring. And here, whenever a wave advances in this direction, this wave is advancing or progressing towards left. So when such wave progresses towards left and strikes this boundary, okay, whenever the wave strikes this boundary, what happens? A wave again approaches this boundary. Here the wave has reached the boundary. What happens? On reaching the boundary, on striking the boundary, the wave gets reflected back in the opposite direction, isn't it? So here the wave is striking the boundary like this. As soon as this wave strikes the boundary, from the boundary the same wave gets reflected back like this, isn't it? So superposition of this wave and superposition of this reflected wave will result in a zero amplitude condition, because these two waves are out of phase by a phase angle of pi. And just now we had studied, whenever two waves which are completely out of phase superimpose each other, we won't see any wave pattern. The result will be zero. So that's why at this position we cannot see any wave pattern here, because at this time the incident wave and the reflected wave superimpose, giving rise to a zero amplitude. And after superposition, the reflected wave will advance towards right. So this is the reflected wave, because incident wave was like this. As soon as this incident wave strikes the or incident on the rigid boundary or close to boundary, it gets reflected, and the reflected wave will be completely out of phase like this, and this wave advances towards the right direction. So this happens in the case of closed boundary. Now what happens in the case of open boundary? So here you can see one ring. This wave is advancing towards that open boundary, which is a ring. Okay. Again it is advancing towards the boundary. Finally it strikes the boundary. So as soon as it strikes the boundary, it gets reflected back like this. And again it's reflected back, and the reflected wave will be of same phase. It will be in phase. See here the reflected wave was out of phase. Incident wave was like this, and the reflected wave is like this. But here the incident wave is like this. Reflected wave is also like this. That means both the incident and reflected wave are in phase. So whenever a wave strikes a closed boundary, the wave is reflected back, and the reflected wave is out of phase with the first wave or incident wave. At the same time, whenever the wave is incident on an open boundary, the wave gets reflected back, and the reflected wave will be in phase with the incident wave. Okay. So that is written here. A pulse incident from the right is reflected at the left end of the string, which is tied to a wall. And note that the reflected pulse is inverted from the incident pulse. See here, this was the incident pulse and this is the reflected pulse. Both are inverted with respect to each other in the case of rigid boundary. And here in the case of open boundary, what happens? The left end is tied to a ring that can slide up and down with friction. Without friction on the road. So now the reflected pulse is not inverted by reflection. Here, this is a ring, and this ring is free to move through the road. So it is an open boundary. And here this is the incident pulse and this is the reflected pulse. So both incident and reflected pulse are in phase with each other. They are not inverted. Okay. Now, another important concept of this lesson is standing waves or stationary waves. So what do you mean by standing wave or stationary wave? From the name itself we can understand a standing or stationary waves means waves are at rest. They will not move. Okay. So a stationary wave is a wave which is not moving. That is, which is at rest. And when do we see a stationary wave or standing wave? When two waves with the same frequency, same amplitude and same wavelength traveling in opposite direction will interfere or superimpose. They produce a standing wave. For example, consider a rigid boundary here, and here also consider a rigid boundary. Okay, there is a string. Just pluck that string in the middle. So waves are produced. Suppose the waves are started from this point, and this wave travel and is incident at this boundary. and this is a rigid boundary, isn't it? So this is the incident wave. Let this be the incident wave. And as soon as this wave touches or strikes this rigid boundary, what happens? It gets reflected back, because we had just studied whenever a wave strikes any boundary, it will be reflected back. What will be the nature of the reflected wave? Is it in same phase with the incident wave, or whether it will be out of phase with the incident wave? See, listen here, it is a rigid boundary. And we had studied just now, whenever a wave strikes a rigid boundary, the reflected wave will be out of phase. So, reflected wave can be represented like this. See, it is out of phase with the incident wave. See, out of phase. Out of phase. Okay, so this is the reflected wave. Reflected wave will be out of phase as that of incident wave. So this is incident wave, and this dotted wave represents a reflected wave. Okay, children. So this type of wave pattern is known as standing wave or stationary waves. So such type of waves can be observed when two waves with same frequency, same wavelength and same amplitude traveling in opposite direction superimpose. So here you can see incident wave is traveling along this direction, that means towards right, but the reflected wave is traveling along in the opposite direction, that is towards left. So when such two waves superimpose in the opposite direction, they will produce a standing wave. So this is the direction, or this is the pattern of the standing wave. Standing wave look like this, and these waves will not move, they are at rest. Okay, now wave traveling towards left. Okay, wave traveling towards left can be represented as, this is A sin kx plus omega t. Wave traveling towards left can be represented by A sin kx plus omega t. And wave traveling towards right is represented by kx minus omega t. Because in the previous slide we had studied, that means in the previous session we had studied, wave traveling towards the positive x direction is represented by A sin kx minus omega t. Isn't it? So positive x direction means towards right, and wave traveling towards negative x direction can be represented as A sin kx plus omega t. So negative x direction means it is the wave traveling towards left. Okay, so wave traveling towards left is denoted by A sin kx plus omega t. It is the wave traveling towards the negative x-axis. And wave traveling towards right is denoted as A sin kx minus omega t, which is the wave traveling towards the positive x direction. And when such two waves superimpose, what happens? We will get a standing wave, and the amplitude of that standing wave will be the sum of amplitudes of these two waves. So the amplitude of the resultant wave y of xt will be the amplitude of incident wave plus reflected wave. Okay, that is A sin kx minus omega t plus A sin kx plus omega t. And this is in the form A into sin kx minus omega t plus sin kx plus omega t. A is the common factor. Now the terms inside the bracket is in the form sin A plus sin B. Okay, sin A plus sin B. Okay, so what is sin A plus sin B? Sin A plus sin B is sin A plus sin B is 2 sin A plus B by 2 cos A minus B by 2. Okay, you had already studied this identity in your maths classes. So sin A plus sin B is 2 sin A plus B by 2 cos A minus B by 2. So just apply this identity to this expression. So you will get the net displacement y of xt is equal to a into 2 sine a plus b by 2. So which is a? Which term can be considered as a? We can consider, yes, this as a and this as b. So a plus b by 2 means kx minus omega t plus b is kx plus omega t by 2. Okay, so here plus omega t minus omega t will be cancelled and we are left with kx plus kx. Kx plus kx is 2kx. 2kx by 2. 2kx by 2 is kx. Okay, so here we are left with kx. So sine a plus b by 2 is sine kx. Now cos a minus b by 2. Next is a minus b by 2. So a is kx minus omega t and b is kx plus omega t. So a minus b is kx minus omega t minus kx plus omega t by 2. Kx minus omega t minus kx plus into plus minus omega t by 2. So here plus kx minus kx will be cancelled and we are left with minus omega t minus omega t. Minus omega t minus omega t is minus 2 omega t. Minus 2 omega t by 2, that is minus omega t. So cos a minus b by 2 is cos minus omega t. Okay, so we can substitute that expression here. Cos minus omega t. And we know cos of minus theta is cos theta. So cos of minus omega t is cos omega t itself. So here we can write cos omega t. That is equal to 2a. This a can be multiplied to this bracket. So 2a sine kx into cos omega t. So this is the resultant wave. So when two waves having same frequency and amplitude traveling in the opposite direction superimpose, we will get a resultant wave and the resultant wave is represented using this expression 2a sine kx into cos omega t, where 2a sine kx, this part represents the amplitude of that resultant wave. 2a sine kx represents amplitude of that resultant wave. And based on this amplitude, we can determine the points of maximum amplitude and the points of minimum amplitude. Okay. So just remember this expression. This is the equation of the resultant wave, and out of this expression, this 2a sine kx represents the amplitude of that resultant wave. Now, nodes and antinodes. So what do you mean by nodes and antinodes of a standing wave? See, I had told you the amplitude of the standing wave does not remain the same. There are certain points with minimum amplitude. There are certain points with maximum amplitude. But because the amplitude part was 2a sine kx, that means amplitude is a function of x. So with respect to x, the amplitude will change. So that is written here. The amplitude of a standing wave does not remain the same throughout the wave. It keeps on changing as it is a function of x. At certain positions, the value of amplitude is maximum, and at certain positions, the value of amplitude is 0. So nodes are the points of zero amplitude. Wherever the amplitude is 0, those positions can be considered as nodes. And antinodes are the points of maximum amplitude. So wherever the amplitude is maximum, those points can be represented by antinodes. So nodes represent position of 0 amplitude and antinodes represent position of maximum amplitude. Okay, so that is meant by nodes and antinodes of standing wave. So if you consider this as your standing wave See, suppose this is a standing wave. Just consider these points. At these points, okay, at these points, what is the amplitude? Amplitude is 0. Okay, so these points represents node because at these points amplitude is 0. Now consider these points. At these points amplitude is maximum. So these points are known as antinodes. Okay, so like this we can represent nodes and antinodes of a standing wave. Now, what is the condition to obtain node? At which position nodes can be obtained in a standing wave? Let's discuss. See, nodes are the positions of maximum amplitude or minimum amplitude. Yes, nodes are the positions of minimum amplitude or 0 amplitude. And you know the resultant wave is represented as y is equal to 2a sin kx into cos omega t. And 2a sin kx is the amplitude of the resultant wave. And nodes represent the points of 0 amplitude. So this amplitudes 2a sin kx will be 0 when the value of sin is 0. And sin theta takes 0 values for certain angles such as 0, pi, 2 pi, etc. So this amplitude is 0 when the sin value takes 0. That means when sin kx is equal to 0. Because 2a cannot be 0. So this term can be 0 only when sin kx equal to 0. And sin kx will be 0 when kx is equal to 0, pi, 2 pi, etc. And you know k is the wave number and this wave number is denoted by 2 pi by lambda. Okay, so instead of k we can substitute 2 pi by lambda into x equal to 0, pi, 2 pi, etc. We can write n pi. This is the general condition. And here x is equal to we can write 2 pi x by lambda equal to n pi. This is the general condition. So here you have a pi, here you have a pi, it will be cancelled. From this you will get x is equal to n lambda by 2. X is equal to n lambda by 2. Where n is equal to 0, 1, 2, etc. Okay, n can take values from 0, 1, 2, 3, etc. So this is the condition to obtain node in a standing wave. When x is equal to n lambda by 2, you will get node. X means the positions. Okay, at which position you can see node. So the nodes can be obtained for the position x is equal to n lambda by 2, where n can take values 0, 1, 2, 3, etc. Similarly, we can find out the condition for antinode, at which position antinodes can be observed. So, you know, antinodes are obtained at maximum amplitude, or antinodes are the points of maximum amplitude. So, you know, our resultant wave is 2a sin kx into cos omega t. And here 2a sin kx is the amplitude. And amplitude will be maximum when sin kx take maximum value. So this 2a sin kx is the amplitude. It will be maximum when sin kx maximum. And what is the maximum value of sin kx? Maximum value of sin theta is plus or minus 1. That is the maximum value of sin theta. And when do the sin theta takes maximum values or plus or minus 1? When kx is equal to pi by 2 or 3 pi by 2 or 5 pi by 2, etc. That means when kx is the odd multiple of or odd integral multiple of pi by 2. Okay, again k is equal to 2 pi by lambda. We know that. Substitute that 2 pi by lambda here. So we will get 2 pi by lambda into x equal to pi by 2, 3 pi by 2, 5 pi by 2, etc. And we can write the general condition as n plus half into pi by 2. n plus half into pi. Okay, that is enough. N plus half into pi. So from this pi and this pi will be cancelled, and from here we can write x is equal to n plus half into lambda by 2. So x is equal to n plus half into lambda by 2. So this is the condition for antinode. Here n will take values 0, 1, 2, etc. So x is equal to n plus half lambda by 2 is the condition to obtain antinode. So what is the condition to obtain node? X is equal to n lambda by 2. What is the condition to obtain antinode? X is equal to n plus half lambda by 2. Okay, so this is about the standing waves or stationary waves. So with this I am concluding my session. Notes of the topic have been uploaded. Please go through it. We will meet in the next session. Till then, take care all of you. Stay home, stay safe. Thank you.